Welcome to the method of Lagrange multipliers, part 4. In this, we will use Python programming to plot the constraints region for the last Lagrange multiplier problem that we saw. I am Ronald Johns. Earlier, in part 3 of the method of Lagrange multipliers, we looked at this optimization problem. We wanted to maximize this function of x, y, and z. X times y times z, and that was the volume of a box with lengths of edges x, y, and z. And the constraints we were given was that the surface area of the box had to be 150, and the length of all of the edges had to add up to 100. We rewrote this optimization problem the following way: maximize that same function, but then we rewrote these two constraints. We subtracted 150 from both sides of this equation, we subtracted 100 from both sides of this second equation, and then we divided this first equation by 2, divided the second equation by 4, and we get xy plus yz plus xz minus 75 equals 0, x plus y plus z minus 25 equals 0. So here are the two equations that we want to solve simultaneously. Find the x, y, and z that satisfy both of these equations. The second equation we can write as z in terms of x and y. Z equals 25 minus x minus y. And then we can eliminate z from this top equation here. The value of z here and here is just 25 minus x minus y. So y times z is y times this, x times z is x times this, and so that equals 75. The second equation, z equals 25 minus x minus y, we're going to keep around because we're trying to find values of x, y, and z that satisfy these two equations. So we don't want to forget that z does depend on x and y, so that we'll get solution points, coordinates x, y, and z, that are in three-dimensional space. Okay, so what can we do going from this set of equations to this system down here? Well, y times this factor is just 25y minus xy minus y squared. X times this factor is 25x minus x squared minus xy. And we'll leave the second equation as it is. So we've simplified the equations, or maybe you'd say it doesn't look very simple, but this will be useful. Now we have an equation here that just involves x and y. So here are the equations we just saw, and let's simplify this a little bit. We have a term xy here, a minus xy here, and another minus xy here. These three added together give us minus xy. And then we have what's left over here, 25y minus y squared, which is here, plus 25x minus x squared, which is here. So this equals 75. We still have that z equation. Z equals 25 minus x minus y also. Okay, going from this system down to this system, we just eliminated the parentheses, no big deal here. And then if we look at this, it looks like we just rewrote that equation one more time down here, didn't we? Okay, so in any case, we see how we got this system. And here is that system again. First equation involves x and y. Let's think of this equation as a quadratic equation in y. And so what we'll do is try to rewrite this in terms of something times y squared plus something times y plus something else equals 0. Okay, so let's see. Going from here down to here, we just rearranged terms a little bit. We put the minus y squared term first, minus xy is the second term here, 25y is here, 25x is here, minus x squared is here, 75 on the right side of the equation. The second equation didn't change. Multiply this first equation by minus 1, and we get y squared plus xy minus 25y minus 25x plus x squared equals minus 75, and z is going to be 25 minus x minus y. So now we have this equation. I'm adding 75 to both sides of the equation. We'll have the first stuff just as we had before, y squared. These two terms can be written as x minus 25 times y. This stuff right here with this term also can be written as x squared minus 25x plus 75, and that will equal 0. The z equation is left unchanged. So we have this system of equations. The first equation we can think of as a quadratic equation in y. We have 1 times y squared plus this stuff times y plus this stuff equals 0. And we can think of this as ay squared plus by plus c equals 0, where a is 1, b is x minus 25, and c is x squared minus 25x plus 75. So then we have the system ay squared plus by plus c equals 0, and z is going to be 25 minus x minus y. So what's going to happen is the following. We're going to solve this top equation for y in terms of x. So for a given value of x, we'll solve that quadratic equation for y, and we'll be interested only when the discriminant b squared minus 4ac is greater than or equal to 0, because that will give us real solutions to the system of equations, which we can plot for this region in three-dimensional space called R3. So using the quadratic formula, we're going to have for each value of x, we're going to have that y is minus b plus or minus the square root of b squared minus 4ac over 2a. And in this quadratic formula, a is going to be 1, b is going to be x minus 25, and c is going to be x squared minus 25x plus 75. So then we have two solutions here if the discriminant is positive, one for the plus sign, one for the minus sign. So let y1 be the solution if we have the minus sign. We'll let y sub 2 be the solution if we have the plus sign. Okay, and so we'll get two values, y1 and y2, for virtually every x value where the discriminant is greater than 0. If the discriminant is equal to 0, we'll just get two numbers here that are the same, one solution in that case. And remember that for our three-dimensional graph, the z-coordinates is going to be given by 25 minus x minus y. And so what we'll do is let z1 be 25 minus x minus y sub 1. Let z sub 2 be 25 minus x minus y sub 2. And so we're going to get one or 2 points, x, y1, z1, and x, y2, z2 in that constraints region that we're trying to graph. One of the nice things in using Python to graph this solution set is that we don't have to do any more algebra. We don't have to find exact solutions to the quadratic equation, because when we do the plot, we're going to change it to numerical values that we can plot. And so we'll just use numerical values all the way through. So we'll start by importing some things. We'll import matplotlib.pyplot as PLT. That's one set of functions from the library matplotlib. We'll import numpy as np, and from the math library we will import the square root function. By using this form of the statement, from math import this, we don't have to use math.square root. The program, when you run it, will recognize that square root comes from this math library. Okay, so what's going to happen? First, we're going to put the coordinates that we're going to plot, later using a scatter plot, in some lists. First of all, initially, those lists will be empty lists for the x coordinates, y coordinates, and z coordinates. Basically, x sub 1, y sub 1, z sub 1 will, maybe I should say x coords sub 1, y coords sub 1, and z coords sub 1 will be the first numbers later that will be in non-empty arrays here. If we look non-empty lists, the second element in each of these, once these lists are non-empty, will be the coordinates of another point in our solution region. Okay, we're going to set our axis limits from a low of -10 to a high value of 30. By doing some computations earlier, which I'm not showing, I found that the entire graph is between these two bounds, lower and upper bounds, for both the x and y directions. So that's why these were set that way. It was not done willy-nilly. You could do it by experimentation, which is what I tried at first. And so then we're going to set the number of subintervals that we're going to have on the x and y number lines. How many x values and how many y values are we going to use? Well, the number of intervals is going to be 1,000. Now, this program went through about 3 iterations. The first iteration, I had x, y, and z loops, all with 1,000 values, and that would mean that I would do about 1 billion calculations. I'm using a desktop computer, so that's not a very good way to do this. After some analysis, which we saw on the previous slides, we figured out that if we have a particular value of y, we can compute the two values x1 and x2. From those, we can compute the z coordinates, z sub 1 and z sub 2, and so we really only needed one loop. And I made the loop go for y. I'm going to make a list for y in np.linspace. Let's remember that np stood for that library numpy. Start with the low value, end at the high value, and we'll have 1,000 intervals in there. Actually, I should say 1,000 points. Or actually, 1,000 intervals would be 1,001 points. We have 1,000 points, so I guess that's 999 intervals. Anyhow, that's quite a few points. We'll set a to 1, b to y minus 25, c to y squared minus 25 times y plus 75. Those were the values, remember, for ay squared plus by plus c equals 0. The discriminant for that quadratic equation is b squared minus 4ac. Here we have if the discriminant is greater than or equal to 0. In that case, we will get real solutions. x1 will be minus b minus the square root of this stuff over 2a. x sub 2 will be minus b plus the square root of this stuff divided by 2a. And in that case, the z1 and z2 values will be 25 minus x1 minus y, z2, 25 minus x2 minus y. Remember that we had the equation z equals 25 minus x minus y on a previous slide, and this is taking into account that we had two different x values, which gave us two different z values. We had x1 and x2 here, but for the same y, which was used for computing x1 and x2. We just have y in this for loop. Okay, and then we will append x1, y, and z1 to x chords and y chords and z chords, and we'll also append x2, y, and z2 to x chords, y chords, and z chords. So we're adding 2 points to our region that we're going to graph. That is because, as we saw, if you looked at the first slide, the region turns out to be an ellipse, and since we were solving a quadratic equation, that gave us 2 x values, 2 which corresponded to 2 points on that ellipse. Okay, so we append 2 points, and then we're ready to go on to see what happens, almost. So here we're not really doing any mathematical calculations. This is the last part of the program. It's just doing the graphics with the points that we've already computed. So I'll let the figure be plt.figure. The figure size will be 8 by 8 in whatever units we're using. Maybe on this screen it's in inches, I'm not quite sure. We'll let AX be the axis that we get by fig.add subplot. It'll be in the 1, 1, 1 position. The projection will be 3D. We're going to get a 3D plot that we can rotate if we want to. And then for all those points given by the 3 lists, x chords, y chords, and z chords, we'll create a scatter plot of those. The points that we plot in the scatter point, as it turns out, lie on a figure that looks like an ellipse. It probably is an ellipse, but it's going to be slanted in 3-dimensional space, as we'll see in a minute. The color I'm going to print this region is blue. The size is 10, which makes each little point fairly small, so the ellipse doesn't look too thick. The markers are going to be small squares, which I guess you won't really see because they're pretty small. And we have a line width equals 0 here, which means that we don't have an edge color for that square marker. We'll set X label, Y label, and Z label to X-axis, Y-axis, and Z-axis. We'll put a title on that plot that says individual black pixels in 3 dimensions. That's actually just slightly wrong because the graph showed up better if I used blue pixels instead. So this should have been blue here. And we notice that we did change it to blue up here. Then the only thing left to do is to show that plot, which is done by this last Python function. And this is the output of that Python program. This is a 3-dimensional plot, and in Python we can move this around to see this 3-dimensional plot from various angles. It appears that the plot is an ellipse, and it's not horizontal, it's not vertical, it's slanted somewhere in between. We used scatterplot to plot each point on this ellipse, and at some point the plot points are fairly far apart, and so we have some gaps that appeared in this graph, but it is excuse me, this is a nice curve that is connected all the way around.